Welcome to the HPC Best Practices webinar series. This series is brought to you by the IDEAS Productivity Project, which is part of the exascale computing project of the US Department of Energy. And this series is a collaboration involving the computing facilities at the Argonne, Oak Ridge, and Lawrence Berkeley National Laboratories. I'm Wesley Marcus from Lawrence Berkeley, and Ashley Barker from Oak Ridge and I will be the hosts for today's webinar. What I learned from 20 years of leading open source projects, and the webinar will be presented by Wolfgang Bungard. Wolfgang is a professor of mathematics and geosciences at Colorado State University. He studied physics and mathematics at the University of Stuttgart and Heidelberg in Germany. He was a postdoc at the Institute for Computational Engineering and Sciences, now the Odin Institute, and Institute of Geophysics at the University of Texas in Austin. He joined the Department of Mathematics of Texas A&M in 2005 and moved to Colorado State in 2016. During his PhD, Wolfgang started the deal.II finite element library that now contains more than 1 million lines of C++ code. He's also one of the main developers of the aspect code, which is widely used in the simulation of convection in the Earth mantle, and also for long-term deformation in the crust. We have issued 212 tickets for this webinar, and all attendees have been muted upon entry. We'll be receiving questions through the Zoom chat and also the Google Doc. I'll paste this address in the chat momentarily. And the webinar will have breaks so Wolfgang can respond to the questions that come in. With that, Wolfgang, I'll stop my sharing here.
Okay, well, thank you, Asmi. Thank you, everybody at the Better Scientific Software organization. As an organization that I really think we need it in our community, and I'm really glad that you guys exist and put on webinars like this. So what I want to talk about today is I am, like many others, sort of an accidental person to fall into open source projects. That was not part of my career plan. I was a graduate student in mathematics, and I just wanted to become a faculty and a professor, and I needed to write some software, and it turned into a career. I've been doing this for over 20 years now. 24 that I started this one project that I'm going to talk about. And along the way, I've learned a lot of things about what works and what doesn't work, and I want to share some of those. I do want to acknowledge that a lot of organizations have funded the work that I have done with many others, particularly the National Science Foundation and the Computational Infrastructure for Geodynamics. I also want to say that this work that I'm going to talk about is not just mine. There are many, many others around the world that have contributed to these software projects, hundreds of people. And many of those with whom I've worked closely over the last 20 years have really informed what I'm thinking about when we talk about open source projects. So I have had the great fortune that I've worked with lots of people who are smart and insightful and have put a lot of thought into communities and how to deal with people. And so what I'm going to talk about when I say that I learned it is as much a reflection as what I've learned from my colleagues and collaborators. So I think they deserve a lot of credit for that. So let me talk to you first where I'm coming from, what my experience with scientific software is. So I started my PhD in 1998, and sort of at the end of my master's project before that, I started a project that's now called deal.II, that today is 1.5 million lines of C++. It's one of the 3 or 4 or 5 large finite element packages that exist out there, things that have meshes and finite elements and linear solvers and everything you need to build finite element solvers for partial differential equations. There are currently 11 principal developers. So these are the people who oversee the growth of this project, who approve patches and so on and so forth. And over these 24 years, about 300 people have contributed to this project. So it's quite a sizable project. It is used by a lot of people, and we know of about 200 or 220 or 240 papers per year that use deal.II. That's probably an underestimate. So that's one of the projects. The other project is called Aspect. That is the advanced solver for problems in Earth's convection. So it's a software package that builds on top of deal.II and simulates how material moves in the Earth's interior. We started this in 2011, about 10 years ago. It is now about 150,000 lines of C++. It simulates convection in the Earth's mantle. It's also used in simulating the deformation of the lithosphere today. There are 9 principal developers and about 100 contributors to this project over these 10 years. So the project that I'm going to tell you most about in the next few minutes is deal.II, simply because it's the bigger one and because it's been around for longer. And I think it illustrates a little bit of like the arc many of these big scientific software projects follow. So before I tell you the details of this project, let me just summarize really what I learned from running these projects. And it is principally that what you really should care about is building sustainable software, things that can last for 24 years. And that in order to do this, you need to build communities. If I had to summarize this on into 2 sentences, really about it's not just about being a good programmer. That a lot of us got into this business because we enjoy programming, but what it really is, once you pass a certain threshold, is that you have to deal with people, and in particular, you have to understand the limitations of people. And the limitations come in 2 forms. One is that 1.5 million lines is a huge system. It's much more than you can ever think about understanding or reading through. It's a complicated combination of things that have to work together, and you have to make it work. You have to somehow wrap your brain around what that means for a system. And the other part is that you deal with people. So the first one is sort of the human limitation about understanding complex systems, and the other one is the limitations of people working in organizations. Okay, so let me start by talking about the technical complexity of these projects, and now let me finally come back to the question of the arc of these projects. So deal.II, like many other large, successful open source projects in the sciences, started as a fairly small, simple project for one person. And if you look at this, there's really a fundamental difference between where deal.II or any of these projects started and where they are now. So in the case of deal.II, I started this in late 1997 as a single graduate student, just for myself. And I wrote about 20,000 lines of code in year 1. Then acquired 2 co-authors, one of whom was a fellow grad student who was sitting in the same room as me, and one at the time was a postdoc in the room next door. And so the world was fairly small at the time, right? So after 2 years, we had 3 people. We had about 100,000 lines of code, and deal.II did not depend on any external dependency. So we did not use any other software projects beyond just a compiler and make. And we also had no external users. So if somebody wanted to implement something, the worst that could happen is that you have to walk to the room next door and figure out, well, how do I do this, or how does it interfere with what you're doing right now? So a very small world, very self-contained, quite easy to manage. And then in 2000, we put it on a website because that's what you could at the time. So 2000 was roughly the time when people started to take the internet, the World Wide Web, as something that you could play with, that as an individual, you can put a website on there. And we really had no intention for this to be anything other than putting on a website because we can. We didn't think about, well, what does that mean if other people start to use it, for example, or do we have to support this? Do we have to document this? So our world at the time was solidly the 3 people in 2 rooms next to each other. And I think that this sort of mindset that we had at the time is actually quite typical of how many scientific codes start, right? Somebody has an itch, and they scratch it by writing a little bit of software for themselves that does what they needed to do, and get a couple papers out of it, or solve a problem that they needed to solve for the work. So that's sort of where we were in 2000. Today, this project has 1.5 million lines of code, and it grows by 100,000 lines per year. So it's a vastly bigger thing. And I think if you want to put this into context, so a good programmer writes between 10 and 20,000 lines of code per year. So let's pretend 20,000 lines per year. Then 1.5 million lines is about 80 years of full-time work. That is much, much more than any single person can keep in their head. There is not one person in this project anymore now who really understands all of the code. There are 11 principal developers. These are the people who approve patches, for example, and many of us have sort of specialized into different areas. So I don't know anything about the continuous integration setup, for example. I don't know anything about the matrix-free framework in deal.II. And the other 10 principal developers also have their own specialities where they know certain parts and not others. I mentioned this before, there's about 300 people who've contributed to this project over the years, and we counted this a while ago. Every quarter, every 3 months, it is approximately 40 different people who contribute code. So it's a sizable organization of people who participate in this as developers. And then there's an even bigger class of people who use this project. So we have about 1,200 people on the mailing list. I don't know how many of those are actually using it every day, for example, but it's a sizable number. It is used in many, many individual research projects, in individual PhD projects where somebody's writing a code for their own needs. But then there are also substantial packages like Aspect, for example, that have their own user communities that build on deal.II. So it is, I think, as far as scientific software is concerned, deal.II is quite widely used. The direction where I'm going with this is that in addition to being a big and complicated organization consisting of many different people with different motivations, it is technically also a much, much more difficult package to deal with today. And so deal.II doesn't just have 1.5 million lines of code, but it uses many other packages itself. And I'm illustrating this here in a graph that shows the dependencies between packages in a collection that is called the XSDK, the Exascale Software Development Kit. It's a collection that the Exascale Computing Project is maintaining, that consists of a whole bunch of software libraries that all somehow depend on each other. And XSDK is a way to make sure that they interoperate today and continue to interoperate, and it provides a way also to build all of these. And deal.II is the one in the red circle somewhere at the top. And what you can see is that each one of these gray lines indicates a dependency. That means that it points from deal.II, for example, to another package that deal.II can use. So the text, of course, is much too small. That's part of the beauty of this graph, because it doesn't really matter what all of these other packages are. But to give you an idea, there's, for example, PETSI and Trilinos that provide linear algebra capabilities to deal-II. There are eigenvalue solvers. There are direct linear solvers, and so on and so forth. So deal-II today builds on, I think, around 40 external packages, quite a lot. And of course, that is on top of just the many, many lines of C++ deal-II has itself, right? So that has implications for the technical complexity behind this project. So in particular, deal-II, like many other scientific software packages, is no longer a collection of subroutines like we used to have in the 1980s and 90s in the form of BLAS and LAPACK. So BLAS is the basic linear algebra subroutine. And it was literally just a collection of, I don't know, somewhere between 50 and 200 individual functions that sometimes called each other, but otherwise were independent of the rest of the software universe. This is not how scientific software looks anymore today. Instead, packages form an interconnected web where packages build on each other, and then on the very top is the application that does something useful based on these packages. And if you wanted to break this down a little bit more, then you would actually see that many of the packages in this graph that I just showed you themselves have modules. So deal-II itself has modules that deal with linear algebra, that deal with meshes, that deal with finite elements, that deal with matrix-free operators, and so on and so forth. And similarly, if you looked at packages like Trilinos and PETSI, they also consist of modules. And a lot of that has to do with the fact that, like I already mentioned about myself, nobody can actually understand just one of these packages individually. Why are things this way? It's because no single developer can know this much, right? So if it takes 80 man-years to write something like deal-II, it must be clear that not a single person can ever read through all of this, cannot remember every detail of this. Things have to be broken down into smaller pieces. And that is certainly true. If it's true for deal-II, it's true for the entire ecosystem that deal-II builds on as well, right? I might be very good at finite element method, but I certainly don't have the background to really know how to write a direct solver or an algebraic multigrid, for example. So in order to deal with my inability to learn all of these things and to implement these, is I need to build on what other people have done. And so things break into smaller components that are built by experts in their own field. So we have to do it this way because we want to use things that are just so complicated that we cannot do it all ourselves. And that is true also for something like BLAS, for example. So in the 1980s, BLAS was relatively simple. You would just, each one of these subroutines fundamentally was just one or several loops that iterate over the indices of matrices and vectors. But today, you have to know cache behavior and maybe multi-core behavior and vectorization instructions and so on and so forth. And yeah, I could write today a 1980s version of the BLAS and incorporate that into deal-II, but that is not appropriate anymore because we know how to do better, or somebody knows how to do better. And the best strategy, of course, is to let that person write an optimized BLAS and I use it. We have to do it this way because we cannot learn this much and we cannot know this much anymore. There are, on the other hand, costs associated with this. And so for our users, the first step always is to have to get through the installation. In order to build the program on deal-II, you have to install not just deal-II, but possibly also PETSI and Trilinos and RPAC and UMFPAC and a whole bunch of other things. And it's complicated to do it this way. It's made even more complicated by the fact that each one of these packages that you have to install and maybe interact with have their own styles of coding and documenting things. They might all have their own way of teaching. So some of those might have tutorials. Others have YouTube videos. Others have only in-source comments and so on and so forth. And so in order to deal with all of these many different packages, you have to learn that they're all different. It's not just that they implement different things, but their style is different. And then for people like me, for example, if you're a package developer, you realize that, well, if you build on other software, that other software is not static. It changes. People introduce incompatible changes. And so what happens to us quite frequently is that we put out a release, and a month later, one of the packages we built on puts out another release that is incompatible, and suddenly you can't install deal.II anymore with the then current version of whatever you wanted to install or build on. So that's aggravating, but this is just the world that we live in. And then as a if you deal with these big packages and you think about this maybe a little bit more from, well, it takes on us this knowledge to interact with other packages and to break it down into modules, for example, you start to think also about, well, how exactly is this technical knowledge preserved in a project? So who knows what, and how many people know what? And in the software world, this is often described as the bus factor. It's sort of a macabre concept. It is the number of people who can get run over by a bus without the project falling apart. And I struggled with whether I really wanted to call it this way in this talk, but this is how everybody calls it. And so I decided maybe I'll go to Wikipedia to find out whether there's a better word. It turns out there's not, but Wikipedia actually has quite interesting things to say about the bus factor. So they define it as the minimum number of team members that have to suddenly disappear from a project before the project stalls due to lack of knowledgeable or competent personnel. And I think that's a really nice description of what it really is about. That if, for example, we have 11 principal maintainers, but we all have our individual specialities, then maybe we can afford, if one of these people moves on in their career, for example, or maybe at one point retires, but that person is going to take knowledge with them. And maybe not every submodule of deal.II is well covered by multiple people. So the technical knowledge that is required to deal with complex systems is really quite an issue. In particular, so Wikipedia also on that page says that somebody determined what the bus factor is for a number of popular GitHub projects, and that for most of these, the bus factor would be 1 or 2. And that means that if these two people happen to decide that they've had it, they're retired, or maybe if they work in academia, maybe they become department head or do any other thing other than being software developers, these projects are dead. So that is a consequence of dealing with these complicated systems, right? That a system that consists of a few hundred or a few thousand lines of code is not that hard to learn for somebody else to take over. If you had a system that has 1 million lines of code, it is very, very difficult for somebody else to take over if the first person is not there anymore. So how do we deal with this issue of complexity? I think the answer fundamentally is quite poorly. I think a lot of folks in our community are aware of it, but we don't really have very good strategies. We talk about software design in ways that we think makes it easier to modularize software, for example, make it easier to learn for other people, at least parts of it. But software design, I think for most of us, is as much an art and a craft as it is science. We don't really understand it. We know what good software design is when we see it, but it's quite difficult to teach it. And I think I'm going to show you 2 quotes that are fundamentally about software design that sort of illustrate the fact that software design is not some technical discipline, but it is about understanding that we write software for people and not for computers, right? It deals with human limitations, human time, for example. So Donald Knuth had this by now rather famous comment that said, we should forget about small efficiencies about 97% of the time. Premature optimization is the root of all evil. The context of that quote was to say that we're not writing software to make it optimal, because that makes it much harder to read, right? It also wastes effort. And maybe a more cogent way of saying that is by Martin Fowler, who says any fool can write code that a computer can understand. Good programmers write code that humans can understand. And that, I mean, these two quotes really embody how I think about software. That when I review other people's contributions to deal.II or Grad, for example, the key piece is to write code that in a year or two somebody else can understand. And whether or not it's fast, or maybe optimally fast, that is not really my first consideration. I mean, it is something that if it later turns out that the code is too slow, we can address this. But the first consideration is that we should write code that we can understand in a year or two, because if we can't, then this part of the software can no longer be changed, right? It implements a certain functionality that presumably other people will want to use, but we cannot change that anymore if we don't understand what it does and how it works. And so the key piece really in software design is to write code that is understandable to humans, that is changeable later on, that is modularized. And what is not understandable, for example, is if you had code that consists of just one giant package that does not consist of submodules, for example. That, of course, also goes to questions like go-to, for example, or the size of functions, right? We need to break things into understandable pieces. So that sounds like it's just a giant mess. It's all gloom and doom, and we cannot possibly deal with software of this size. And I think that's really not the message that I want to convey. I think there are really good approaches that we've learned over the years. So, for example, there are many good technical solutions that work around human limitation. So, for example, we forget function names. And I mean, that is certainly true for libraries like BLAST that had to encode everything into 6-character function names, but that's true also for deal.II that has literally tens of thousands of functions in a public interface that you could call. And one of the ways we as humans have learned to deal with this, that we have integrated development environments that have autocomplete, right? You start to write the name of a function because maybe that's the part that you remember, and then you just hit Control Space, and it autocompletes the name. And as a consequence, for example, in our practice in deal.II, we're quite happy to use fairly long function names that are descriptive because you don't have to write it all anymore. You just autocomplete it. Another human limitation is we make mistakes all the time, right? We have bugs in our code, and we break code later on, and we deal with this by writing test suites. So deal.II has a test suite that has about 12,000 or maybe 13,000 tests by now. And so fundamentally, every comma that you ever want to change needs to run through the entire test suite, so we can make sure that whatever we change does not actually break something. We also have learned how to do peer review, right? That not every patch in deal.II, whether it is from a newcomer or from me, has to go through peer review where somebody looks at it and thinks about, well, is this code correct, for example. Dealing with software installation, for example, is repetitive and boring. So we use package managers, and we have learned that we can't keep things in sync. So if there are two different places that somehow depend on each other, we have a habit of just changing one and not the other. And the most common place where that happens is with documentation, that we cannot keep a separate manual in sync with the code. And as a consequence, we have developed tools that can extract documentation from the code itself in such a way that we really have to change only one place. And so just to give you the names of some of these tools, if you ever wanted to look them up. So for autocomplete, for example, I use Eclipse. Other people use Visual Studio, yet others use Qt Creator. There are many many IDEs that that read and understand code and can use autocomplete, can look up where a function is defined, can show you the documentation of a function as you call it, and so on and so forth. For testing, there's C-Test, there's Google Test, there are many other testing frameworks. For code review, we use GitHub. For continuous integration, there are GitHub Actions and Jenkins. For package managers, you can use CMake, Stack, many Linux repositories that make installation a lot easier. For documentation, we use Doxygen. And there are other solutions for other programming languages. But so these are all technical solutions that fundamentally address human limitations. There are other categories of things that for which there is maybe not a technical solution that does the work for you, but there are collections of best practices. So for example, there are good descriptions of how you should write documentation. There are good descriptions of how to write teaching materials. There are good descriptions of how to onboard new people. I'm going to come back to that later in this talk. And then there are coding styles, software patterns, naming conventions, and so on and so forth. And it is something that I do with every generation of my graduate students, that we read through books, for example, that cover these sort of topics, because they really, I think, make the difference between somebody who's a good programmer for an individual project as opposed to somebody who knows how to contribute to a much bigger project. You need to have sort of a vocabulary, for example, about software patterns that makes it easier for you to document things in a way that is understandable to others because you're using the same words. Or you have to have an understanding of why naming conventions are useful, because it makes it easier for other people later to read your code. And so among the things that I have read with my students is Code Complete, for example, Steve McConnell. It's a thick book, more than 1,000 pages. Maybe didn't have to be quite that thick, but there are other books in the same direction that discuss these sort of best practices. For design patterns, there's the book by the Gang of Four. The first author is Gamma. There are many others that have appeared in the last 20 years on this too. There is a book by Carl Vogel about producing open source software that talks a lot about sort of organizations. And then a lot of us also, when we interact with other projects, when we build on other projects, we take some time to read through their documentation and tutorials with an eye towards, well, how do they do it, right? What can we extract from how they do it for how we could do better for ourselves? And then I should be remiss if I don't also mention the Better Scientific Software organization, the organization that puts on this webinar, that has a lot of resources in this regard as well. So there are a lot of really good technical tools and best practices that address the issue of dealing with technical complexity in software projects. So just to sum this up, this part, I think that building workable scientific software projects is really about managing the complexity, and managing the complexity in the sense that humans have limitations around complex systems. And that is really no different from, let's say, how pilots interact with airplanes and how city managers think about the electric and sewage system in cities, and how, let's say, an architect would approach building an airport. These are all complex systems that go far beyond how an individual can understand it. And so you have to break it down into smaller units that are understandable, extendable, workable. So a large amount of time really goes into breaking things into manageable chunks, writing documentation specifically about the interfaces of different modules, writing teaching material, building infrastructure that allows you to build these projects. My perspective is not so much that the issue is with the technical tools. There are really very good technical tools and best practices, but it's really about the human ability to understand and deal with complex systems, and how how we make it work somehow. So this was what I had to say about the technical complexity, and I want to move to the human complexity, but this would also be a good place to see if there are any questions.
Yes, we do have some questions here in the Google Docs. So let me go here. So first question, what happened to deal.II?
Yeah, deal.II was built by another set of 3 grad students, and they in their research groups continue to use it, but it has not become an open source software project like deal.II has.
Okay, another question here. How do you balance time between contributing to open source projects and the work responsibilities?
I will come back to that in the second part here.
Okay, so then let's go for the next question then. Did you learn software development by use, or did you take any professional software development classes?
No, I'm self-taught in this regard. So I studied physics and then was a grad student in mathematics, and then eventually became a faculty in mathematics. And so I don't have a software design background, but I spend a lot of time educating myself. I can't say that I'm uneducated about the topic, but I have no formal education. I don't have a degree.
Wolfgang, how are you addressing the transition to GPUs?
Yeah, I don't, right? I personally don't. I don't know anything about it, but other people in the project do, and they are addressing it. Yeah.
Okay, so there are 2 more questions here. So before we continue, did you stumble on any anti-patterns that you would want to share?
That's probably a too technical part to discuss here, but I mean, yeah, we make mistakes.
Yes, so then you can address in the question and answers after later. Yeah. Let's take another question here. How did you manage to find 11 developers?
I'm also going to come back to that in the next part.
Okay, so for the sake of time, people are typing, but for the sake of time, please continue.
Okay. Okay, so the other part that I want to talk about is that these projects consist of a lot of people, and how do you actually deal with this? And so let me just outline sort of the problem that we have there. A lot of research projects, or a lot of scientific software research projects. So there is no documented solution that you just have to implement. And as a consequence, the people who work on these sort of projects are oftentimes not software engineers or computer scientists, but are mathematical, physical, chemical scientists themselves. So the things that they implement, they are both the developers of new research methods and software engineers at the same time. So that makes one part already quite difficult. The other part is most of the participants in scientific software projects are temporary employees. I should have put quotes around employees because sometimes they work at national labs, for example. But in any case, they're often graduate students and postdocs. So the time that they spend on working on a certain project is quite limited. There are also often unpaid volunteers, people from around the world connected through the internet, who are graduate students at other universities, for example, who I have absolutely no control over. So they're unpaid from my perspective. I mean, they might be paid for the work, but I don't pay them, and they volunteer to the project. And finally, they're generally people without a formal computer science education. And so there's a lot of challenges that come with this. So let me go through this. The fact that most of these people are working on our project on a strictly time-limited basis means that for the people who are senior leaders of projects who are there on a more permanent basis, they spend a lot of time onboarding new contributors, teaching them how to write better software, how to participate in a bigger project, how to use GitHub, for example. And there's a lot of teaching and mentoring that is necessary because we have people who come and go all the time, right? It also means that there's a higher importance on code review, for example, that if you deal with people who don't have a formal CS education and are new to a project, they don't know our style yet, for example, and so you have to spend a significant amount of time on reviewing code. Also, if you're a graduate student and your job is to write a PhD thesis and then maybe get a job in industry, you don't quite feel the same level of ownership in a piece of code than maybe I do, right? This is my baby. I started this 20-some years ago, and I run it with some of my best friends now, and so I have ownership and pride in this project. But somebody who only needs to get a job done may not quite have that ownership and pride. So leadership in these sort of situations needs to make up for a lot of experience and quality. And oftentimes that means maybe we accept this code now, and then you as a principal developer go back and fix it up or document it better. These sort of things. The fact that we deal with volunteers that are not paid by our project means that in practice, it is often quite difficult for us to establish roadmaps. So when we write our proposals, for example, to the National Science Foundation, it's not so easy for us to say what will actually be done in the next 5 years, because most of the development is by somebody who has an itch and scratches it for writing a piece of functionality and contributed. I can't tell anybody what to do, right? They're not my employees, and I have to treat them from a very different perspective. I have to accept that they do what they want to do. That again puts a lot of responsibility on the senior leaders, right? Same issues, right? Constant onboarding, a lot of teaching, mentoring, a lot of code review. And it also means that the senior leadership deals with a lot of the key infrastructure improvement, things that are too big or too technical for somebody who comes in as a grad student somewhere to provide. Because I don't know, think about, making it run on 10,000 processors and building a data structure. That is something that needs somebody who has a longer term horizon on this project. The other part is volunteers come and go. And so a lot of the work that we do is trying to really grow the pool of volunteers, making sure that for everybody who leaves, there is one or more who are willing to join, right? And so we spend a lot of time mentoring people and trying to make sure that they get credit for what they should get credit for, because that is a way to grow the pool of volunteers. And then there's the issue of having to deal with the principal developers themselves. So if I think about myself and my 10 colleagues, for example, so we fill many different roles, right? We're not just managers in the human resources sense, but we manage the technical infrastructure. We maintain the institutional knowledge of how does this whole project work together. We spend a lot of time onboarding and mentoring contributors. We review patches, and then we also do technical work that requires 10 years of experience or 20 years of experience with a piece of software. And all of this is made more difficult because in academia or in the national labs, the people who typically run scientific software projects, these people typically also have to manage their own careers, right? So as a faculty, I have to teach, I have to supervise graduate students, I have to publish. Similar constraints are on people who are permanent technical staff at the national labs or in industry, for example. So we have to find funding for our work. We have to document our work. All of these sort of things put a lot of demand on principal developers' time. And that I find difficult to manage. For myself, it is also very difficult for me, for example, to ask my fellow principal developers for their own time, because I know that they also struggle with this. At the same time, if you're a person like me and you like to interact with other people, at the same time also like doing technical work, this is not such a bad job, right? I've made a good career out of something that I really enjoy doing. So the diversity of this job is something that I really enjoy. So I was asked whether I can distill some of this into a few recommendations. And so let me go through just some of those. So for the technical aspects, the part that I talked about in the first part of this talk is there are some really good technical tools out there. So IDEs like Eclipse or Visual Studio, for example, and you should really be using them instead of Emacs or VI that are fundamentally just glorified editors. Tools like Eclipse understand a million lines of code and understand what the member functions of a class are in ways that Emacs and VI never can, and never will build to either. You should use things like CMake instead of write your own make files. You should use tools like Doxygen instead of writing your own documentation tools. You should use GitHub for peer review of code, and you should be teaching all of these tools too, right? So, I mean, maybe I have used Emacs since 1991. I really know every keystroke in Emacs, but I can't, or I try not to use it when I interact with students because they will never have that technical expertise to work with Emacs the way I do. And as a consequence, I really try very hard to teach myself tools like Eclipse because then I can teach them to the students, right, or to collaborators. And the same is true that I might be a good programmer, but it certainly helps me to read up on best practices because then I can teach these to other people as well who may need the expertise codified in books because they do not have 30 years of programming experience yet. And for the human aspect, I mean, one of the things that I always tell people who are interested in joining open source projects is to really think about, is this compatible with your career aspirations? I mean, some of us spend inordinate amounts of time running these sort of projects. That is something that we can only do because we have found that it is compatible with what we do in our careers, because it's appreciated by our departments or our universities or our employers. And only then can you actually make that step and say, yes, this is a project that I want to lead and on which I'm willing to spend 20 hours a week. If you do this step, understand that where people are coming from, that you're not leading a software project in the industrial sense, right? You're not a manager. Most of the people you interact with are there because that's what they enjoy doing, but they're not paid by you. And so it really takes understanding that people come from different directions to this project and taking them where they are. You will spend a lot of time mentoring, and you will have to, if you want this project to survive long term, try to be welcoming to newcomers and be generous with praise. And so that's the question coming back to how did I find 10 other principal developers? These are all people who started to use the project and who saw the value and saw value in contributing because their contributions were appreciated. And so as a project, we talk about this all the time, that we really try to be welcoming and generous to people beyond what maybe is necessary, because that is what allows us to build a community around it. So just to conclude this, and then we have 10 minutes for more questions. The way I see scientific software packages today is that they're fundamentally different from sort of the small academic codes that we all write for our own purposes. And that the issue is principally about the complexity, the technical and human complexity of these projects, because they're so huge, both in terms of the code base and the number of people involved. And so a lot of my thoughts around these sort of things is not just about the complexity itself, but how humans deal with this complexity. How can we figure out technical and human ways to break things down into chunks that we can understand and deal with? And that at the end of the day, being a successful software manager in the scientific software realm really requires that you understand that it's about humans, and that humans come with different skills and different motivations, and that you have to take them where they are. So there are two other pieces of information that I would like to link to. One is a blog post that I wrote a while ago for the Better Scientific Software blog. The link is there, and you all have access to the PDF files. And then my former postdoc and now good friend and colleague Timo Heischer and I wrote an article for Computational Science and Discovery about this as well. And I think with that, that would be a good place to come back to questions.
Thank you, Wolfgang. Very nice. We do have some questions here. Let me see here. As a physicist and mathematician, do you produce more in science or computer coding? How can you reach a balance between being productive in science and coding with the best practice?
Well, so I'm really fortunate in my career that I have a permanent position in one department, but in reality, I sit between a whole bunch of departments, right? The math department pays my salary because I think I also produce good mathematics, but I work with people in the geosciences and I have a courtesy appointment in the geosciences department, and I work with people in physics and in chemistry and a whole bunch of other places. And so I don't think of myself as somebody who's tied down to one specific discipline. I am somebody who, I think of myself as a technology transfer agent, right? I talk to my math colleagues developing new finite element schemes and then coming up with ways to implement them in such a way that people from many different disciplines can use them. And for me, that's a beautiful place to be. And it involves learning from people in many different disciplines, and it involves some human resource management, and it involves some programming, and it involves a little bit of mathematics and a little bit of chemistry and physics, and so my world is very broad. I'm not somebody who goes really deep into stuff, but that's just because that's what I'm good at. And it's all a balance, yes.
Okay, another one here to paraphrase Seymour Cray. Would you rather write software with 2 professional programmers or 100 volunteers and grad students?
Well, I mean, this is a funny question, right? I think personally, I enjoy the interaction with people. It makes me happy to have 100 volunteers and work with them and teach them. I'm, as a professor, I'm a teacher, right? And I enjoy that part too. In practice, if you need to get something done, next week, then the 2 professional programmers are probably the better choice, right? But that is not my choice. I don't have the money to pay 2 professional programmers. The National Science Foundation does not give money at a level that would allow any of the projects that are out there to do this. That's not part of our world. I think if you wanted to be part of that world, the national labs, for example, would be an excellent place. If you think about the exascale computing project, they do have money for these sort of things, but that is just not part of academia.
All right, so let me, okay. So do you see the current level of package complexity as a necessary feature to achieve modern functionality, or as an undesirable side effect that we are realizing post facto and we could aspire to simpler structure in the future?
No, there's absolutely nothing you can do about it, right? I mean, at the time, so I keep coming back to BLAS because BLAS is, to me, one of the very first, successful long-term projects that have survived out of the era of the 70s and 80s to today, defining an interface that has been essentially unchanged since the 1980s. And I mean, there are other people who are probably more qualified to answer this, but I would expect that the original BLAS had maybe, somewhere between 2,000 and 5,000 lines of code. It was not terribly difficult. But if you think about how this looks like today, I'm pretty sure that today's implementations of the BLAS have tens of thousands, maybe over 100,000 lines of code, simply because that's how complicated our processors have become. And I really don't see how we could do any different, right? That the software has become complicated because the methods are complicated. I mean, we can solve PDEs today, that are coupled, and we can do this in parallel with high order methods on complicated meshes with hanging nodes, and an algebraic multigrid preconditioner. And I mean, these are all things that weren't around in the 1980s, and that's what drives the complexity, is because the methods that we have are just so much better and so much more complicated, and the software simply reflects that. It's not like we made a mistake. This is just what it is.
And Wolfgang, how do you avoid micromanaging new students and the code they write?
Yeah, I don't know. You probably need to ask my students about this. It's difficult, right? And I think, I mean, that is not specific to this particular area, but if you have 30 years of experience doing something, a lot of things you can do faster and better than a student who does not have that experience. And it requires letting go. And I think, I didn't mention this, but I think a lot of the successful software packages are written by people, let's say, a lot of the successful packages with big developer communities are written by people who have the ability to let go, to say, yeah, I started this, and I'm very attached to it, but I'm happy to let somebody else take this piece. And that's really difficult, right? I mean, you're emotionally invested in your software, and it's difficult to let somebody else deal with it. And I think some people are better than that than others. And the people who do not have the ability to let go are fundamentally the ones who, at the end, continue to work on projects that only they and maybe 2 or 3 others are working on, as opposed to these big developer collaborations that we have in deal.II and Aspect, for example.
So if you're starting deal.II from scratch, would it be reasonable? What would you do differently with your current knowledge?
Yeah, that's probably a good question. I mean, people ask, for example, would I use a different programming language? And I think probably not, because the entire ecosystem in high performance computing is written in C and C++ today. So there's really no good reason to choose anything different. There are some technical decisions that I think we would do differently. But one of the things that I continue to be surprised by is that we, by and large, chose fairly good software design. There are not many places where I would say, oh, this was the wrong abstraction, or these 2 classes should not have been coupled. And so maybe I'm biased because I wrote a lot of the fundamental pieces of the library, but I don't really have the impression that we should do something vastly, completely different. I would probably today not build our own linear algebra, but I would simply build on something like Petsy or Trillimas, except that didn't exist in 1997, or wasn't as accessible in 1997. And so we have our own implementation of linear algebra, at least for a single processor jobs. That I wouldn't do anymore.
Yes, for the participants here, we'll ask Wolfgang to go through the Q&A later and check the answers. But let's take, I think we have time here for another question. On the focus of academia to publish papers over publishing code, how do you handle this personally and with your grad students? Also, how do you handle the training requirements internally? Do you use existing resources like MOOC, or do you do one on training or something else?
Okay, so let's go to the papers first. So if you want to have a successful career in academia, then publications is the quantity that matters, right? And so I am fortunate because I don't just build deal.II, but I use it for collaborations with people in other disciplines, and a sufficient number of publications has come out of this to allow me to have a good academic career. There is an alternative path. So if you can demonstrate that whatever package you have is, really widely used, then that is something that the NSF, for example, cares about and funds. And I suspect that in academia you can get by with some fewer publications if you're able to bring in big grants. So deal.II, for example, is currently funded by a grant to Timo Heister and myself that pays us 1.8 million, not us, but that gives our universities $1.8 million. That's quite a sizable grant from the NSF, and our departments appreciate that. So that is certainly helpful in having a decent career. We do make sure, several years ago, we made the decision that we should write a paper about every release. And the rationale for that was not that we think that what we do in one release from one release to the next is scientifically super interesting, but it is that it gives us a way to make everybody who contributed to one release the opportunity to be co-author on this paper. So everybody who contributes in some substantial way to the development of the library can be a co-author on one of those papers. And these are generally quite well-cited papers. I mean, they get hundreds of citations in the next 2 to 3 or 4 years, and that is something that matters to a lot of people, because that helps them explain their careers to potential employers. As far as training is concerned, deal.II has a reputation, I think rightfully so, as a very well documented piece of software. And we spent a large amount of time writing very good documentation, writing tutorials, creating video lectures that explain deal.II to other people. That's part of what you need to do if you want people to learn the software without having to ask you a lot of questions. Because the one thing that does not scale is if you have 1,000 users and they all have questions and ask them on a mailing list. No volunteer organization can muster the effort to answer all of these questions. What you need to do is to have all of these answers written in places where people can find them themselves. That's fundamentally what it comes down to.
Just bear with me here. Since you mentioned the National Science Foundation, there is a question here. Should the Department of Energy change funding to better support your ideas?
Yeah, absolutely. Of course, they should give me money. What a question. Arne, do you have an in somewhere? I mean, I have thought about this for a long time, and I have reviewed for the National Science Foundation on many occasions, for example. So the National Science Foundation has understood over the last 10 or so years, or maybe 15, that software packages like deal.II are fundamental infrastructure in the same way as telescopes and particle accelerators are, that they support a lot of secondary science, right? That we have the opportunity to provide you with a software tool that does 90% of what you need to simulate the growth of plant roots, or the oscillations in the magnetosphere of the Earth, right? These are the things. And from the perspective of the National Science Foundation, there is the choice of either letting everybody write their own software and be not quite as productive, or to support projects like ours, write documentation, write tutorials, and so on and so forth, so that people have an easier time to do the science they want to do. In much the same way as you could say, well, all of the astronomers, get a little bit of money to build their own telescopes. Well, you're probably not going to get quite as good science out of it. And I think the National Science Foundation has understood this, and DOE has understood this to a much bigger degree as well. So I'm not terribly concerned right now that that understanding doesn't exist. The problem with the National Science Foundation, I think, is that we have to go through peer review with our proposals every 5 years, because there is no key list of packages that NSF would consider a critical infrastructure that gets sort of a base funding. And I think that makes it quite difficult for a lot of us to really have long-term planning stability, for example, long-term, just a foundational level where we can say, yeah, I know I can engage in this for the next 10 years. That part doesn't exist, but that's just how it is. I think, I mean, if the question is, should DOE support deal.II, that is a decision that DOE needs to make.
Okay, so let me share my screen here just to close. Thank you, Wolfgang, and the participants. Thank you all. Again, so we'd like to improve the series. Please give us feedback. I have already pasted this link in the chat. The slides are already available. The recording will be available later today. And with that, I'd like to announce the next webinar in the series. It's going to be about a month from today. Migrating to Heterogeneous Computing, the lessons learned in the Sierra and El Capitan Centers of Excellence. And this webinar will be presented by Dave Richards from Lawrence Livermore National Laboratory. And we are already accepting, it's already open for people to register. Thank you again, everybody. Thank you, Wolfgang.
My pleasure. As a community, I care about it. It's fun to talk to all of you.